Hi, I am Dr. Sungjae Kim, a professor of mathematics at Mississippi State University. You are watching lectures on numerical analysis, which are based on my lecture note, numerical analysis and applications. Let's go to chapter 1. In this chapter, we'll review calculus and linear algebra, and we consider computer arithmetic and convergence. And at the end of the chapter, we'll see programming with MATLAB or Octave. Octave is a free alternative to MATLAB. Here we have section 1.1, review of calculus. A function f is continuous at x0, a point, if this equation is satisfied. First of all, the limit should exist as x approaches x0, and the function must be defined at the point at x0, and the point value must be same as the limit. By using epsilon delta argument, we can define the continuity more rigorously. For every choice of epsilon positive, there is a corresponding delta positive, such that when x minus x0, the distance is bounded by epsilon delta, then f of x and f of x0, the distance is bounded by epsilon. Okay, that is the definition of continuity using epsilon delta argument. Okay, we consider here examples of discontinuity. Okay, here, and this is x coordinates, and now that is x0. And left hand side has a limit here now, and for right side of x0, the function is given in this way. Then here, the function has a jump, so that this kind of discontinuity is called a jump discontinuity. Okay, and around x0, now the value may go to infinity, and one side or both sides. And for example, the other side, now given in this way, then it is going to infinity, so it is called infinite discontinuity. And now at x0, the function may not be defined, for example, like that. So here, if x0 is here, the function value is not given or assigned somewhere else, then we can define the point value here, or replace this value to become this one, so that this discontinuity is removable. And so that name came removable discontinuity. Okay. Now let's consider infinite sequences of real numbers. Xn is an infinite sequence, and it has the limit x if for every choice of epsilon positive, there is a corresponding positive number, capital N epsilon, such that whenever n is larger than capital N epsilon, the distance between xn and x is bounded by epsilon, except possible final numbers. Later on, once n is larger than capital N epsilon, then all points, so infinitely many points, are near to x. So for arbitrary choice of epsilon, you can find such n epsilon so that infinitely many later points are near around x. Then we say x is the limit. In this case, we use the notation limit as n approaches infinity, xn equal x, or we can use this one, xn approaches x as n approaches infinity. Okay, this theorem is saying that here two equivalent statement, f is continuous at x, and for a convergent sequence, this one is satisfied. Limit as n approaches infinity, f of xn is f of x. Okay, that convergent sequence means that limit as n approaches infinity, xn equal x. Right? For such sequence, now it is satisfying this equation. Okay, x is the same as that one, so the right side can be written in this way. F rather than x, we can use limit n approaches infinity and xn. Okay, so here this term is same as that, and that means here limit and f can commute, so that for this one, first limit is applied to the sequence, and later once f is applied, for this one, for every point, now function value is applied, and for those function values we are taking limit. And either way, this value must be the same once the original sequence is convergent. And this is happening when f is continuous, and now also if f is continuous, then now this is also true. So if this is true, then f is continuous. If f is continuous, then that is also true. They are equivalent. Okay. Differentiation. Here, okay, now f is a function defined on open interval containing x0, and the function is differentiable at x0 if this limit exists. This quotient represents the average slope between x and x0. Now, as x approaches x0, once the limit exists, then that is the derivative of f at x0, and we are using such a notation. Right? You learned this one in the beginning of calculus. Once a function is differentiable at a point, then the function must be continuous at a point. But the converse is not true in general. For example, for this function, fx equals x absolute value, and this is continuous. Pictorially, we can make such kind of a picture that is continuous at here the origin, and however, now it is not differentiable. That quotient, if you measure this quotient from left hand side, once x is approaching from the left, then this quotient slope is -1, so that limit must be -1. If x is approaching from right side, then this quotient must be 1, so that the limit must be 1. So left limit, the right limit are different, which means that the limit doesn't exist. So here, at this point, is not differentiable. Okay. Okay, intermediate value theorem. F is continuous. This notation means continuous over interval A and B, closed interval. Now, there is assumption F is continuous over a closed interval. And K is a number between f of A and f of B. Then there exists a number C between A and B for which f at C is K. Let's consider an illustration. Okay. Here, there's x coordinates and y coordinates from A to B. Okay, A to B. Now, f of A, that one, and f of B. And we assume that here f is continuous. So that let's make here a graph. So that is now f of A, and that is f of B. Okay. So here that is f of B, and that is f of A, right? If we choose any value k between f of A and f of B, then that is point C between A and B such that at C the function value is k. We can easily check that through by using a horizontal line here, then mid here, so that if you are choosing now C here, then f of C must be k. That means that here between f of A and f of B, this interval is in the range of the function f. For every k between f of A and f of B, there must be some point C between A and B such that f of C is same as k. This intermediate value theorem is quite useful. Okay, let's see this example. Show that this equation has a solution in the interval 0 and 1. To solve the problem, we define function f of x, moving this 1 to the left-hand side, and we define that this one is f of x. So the solving this equation is the same as finding 0. fx is 0, right? And to check if it has a solution between 0 and 1, we just check values at 0 and 1. Okay, f of 0, f at 0 is now 0, 0, 0, and minus 1. Okay, at 0, the value is minus 1. Now, how about f at 1? At 1, 1 minus 2 plus 3 minus 1, so that it is 1. Pictorially, right now, at 0, the value is minus 1. And at 1, okay, this is 0 in x direction, this is 1, and the value is 1. Okay. So that now, between 0 and 1, here left end point, the value is minus 1. Right end point, the value is plus 1. Now, this is polynomial, so it is continuous. So it must be here given in this way. Somewhere it should hit x-axis. That's basically the C. Okay, so pictorially is quite clear. This theorem, intermediate value theorem, is quite useful to check if a solution exists inside the prescribed interval. Rolle's theorem. We assume f is continuous over closed interval AB, and f is differentiable. And furthermore, we assume f of A is same as f of B. Then there is a number C between A and B such that f prime c is 0. Okay, let's see here an illustration. Okay, this is now x-axis, and here we have a, here we have b. Function value at a and function value at b are the same. Okay, so it's same, and now f is continuous and differentiable, so that the curve must be smooth. Okay, let's say such smooth curve. Then for this case, we can easily see that here there are 2 points right now, such that at the point the slope is 0. So that this can be C and that can be another C. Right? Existence means that at least one such a point exists, so that for this case more than one. So can say just the existence. Okay. Okay, now we have mean value theorem. F is continuous over closed interval AB and differentiable. Then there is a number C between A and B, such that that is average slope, and this is derivative at C. So the instantaneous slope at C is the same as the average slope. The difference between mean value theorem and Rolle's theorem is here. In Rolle's theorem, assume this f of a and f of b are the same. Now for mean value theorem, such assumption is not there. So mean value theorem is more general case. So Rolle's theorem is a special case of the mean value theorem. Okay, pictorially, now here, okay, here A and B, and here that is A, that is B. Now f of A and f of B, and f is continuous and differentiable. So let's connect with a smooth curve. Okay, that is, assume this is the graph of f. Now, and that quotient right side is here, that one, the average slope, and by saying a triangle, here, that change is this top, and this denominator is this change. So here, that average slope is this one. And there is at least one point C such that the slope at C is the same as average slope. Apparently, if you are moving this one and parallelly and becomes a tangent line like that, so that we have here the such C and at two positions, so that this can be C and that can be another C. Okay. Now this can be written in this way. First we multiply b minus a both sides, and then move f of a the other side, so we can get here. Let's see this example. F of x is given x plus sine x and defined on 0, 2. We want to find the c, which assigns the average slope. Okay. In this example, we want to find the c used in this mean value theorem. Okay. Here we have a maple code. A is 0 and b is 2. Function is defined in this range, and colon equal means definition, defined. And average slope is now this one, and this blue writing is computer output. I implemented up to this one, and here there is output. And this sign means the last output. So for that one, we try to make floating point value. And this one is same as that. Now, we define equation as f of x equal, f prime x, like over there. F prime x is equal the average slope. So that's output. For the equation, we solve it for x. Then solution will be c. And for the last output, here we can get floating point number that is about 1.1. Now here, this portion is for plotting. And we see here the plot. And f of x is this one, curve. And then now that represents the average slope. And this point is c, is about 1.1. And this line, tangent line, is parallel to this line. Okay. Extreme value theorem. If f is continuous over closed interval, so here the condition is f is continuous and over the closed interval, then there exists C1 and C2 and in AB such that function values are between f of C1 and f of C2. That means that f has minimum and maximum value over the closed interval. In addition, f is differentiable, then C1, C2 occur either at the endpoints of AB or f prime is 0. And that such point is called critical points. Okay, let's see this example. Find the absolute minimum and absolute maximum values of the function on the interval 1, 2. So here, again, we have a maple code. A is 1, B is 2. And now f is defined. And f of A is f of A. At A, f is evaluated. And f of B is f of B. Now here, we try to get derivative. So that is fp. And fp is given over there. Now, for fp, we solve for x. So try to find the critical point. Okay, so we got that one. Now, the last result. So function value is made here. fc is now critical value at c. And so we have two boundary values and one critical value. And among them, maximum is global absolute maximum. And among them, the smallest one will be global minimum. Here pictorially, and that is original function f of x, and that is its derivative. So once we solve the derivative is 0, then we get this value. And from here, now you can get function value. So that is now f of c, and that is f of a, f of b. Apparently, f of c is minimum, and f of b is maximum. Right? Okay. Now, by using Rolle's theorem, you can prove this generalized Rolle's theorem. F is continuous over the closed interval AB and n times differentiable. And Also, f is 0 at n plus 1 distinct points, x0 to xn. They are between a and b. Then there exists a number c such that f nth derivative at c equals 0. In the course of numerical analysis, and there is no problem using this generalized rules theorem, but for some advanced numerical analysis, you may be using that theorem. So that's the reason I included this generalized rule theorem. Okay, that's the end of the first part, and we'll continue in the second part. Thank you.